All right, diving in today, folks, getting into some naive Bayes classifiers. Maybe sounds a little bit techie at first, but trust me, this stuff's everywhere, even if you don't realize it. Like, ever wonder how your email knows what's spam and what's not? Or how those document sorting features work? Well, a lot of times, you can thank naive Bayes for that.
It really is amazing, isn't it, how this deceptively simple method can handle such a wide range of classification tasks. And the cool thing is, for this deep dive, we've got some really great resources that make it all pretty clear.
Yeah, we're looking at the Scikit-learn documentation for like the nitty-gritty practical details. For the big picture, we've got Wikipedia. And then to like really get into why this thing works, which is a bit of a head scratcher at first, we've dug into some research papers too. So today we're going to like break down those core ideas, see what it's good at, where it struggles, and basically figure out how can something this simple be this powerful.
It all starts with probability, actually. And a pretty famous theorem, Bayes' theorem, maybe rings a bell from stats class. But basically, it gives us a way to update our beliefs based on new evidence.
So imagine you have a hunch about something, right? And then you get some new information. Bayes' theorem lets you adjust that initial hunch based on this new info. And in classification, that hunch is all about the probability of something belonging to a certain category.
Exactly. Like, is this email spam or not? Is this news article about sports or politics? And we use the features, the things we observe, to figure that out. So the words in an email, the topics mentioned in an article, those are our features.
Okay, so we want to know how likely something is to belong to a class based on what we see. But then there's the naive part of all this, right? What makes naive Bayes so well? Naive.
The naive bit comes from the assumption that all those features we're looking at, they don't affect each other once we know the class. Like, if we know an email is spam, naive Bayes assumes that the word free being there has nothing to do with the word money also being there.
But those words often show up together in spam, right? So it sounds like it's pretending things are more independent than they are in real life.
You got it. It's a simplification. But without it, things get really messy really fast.
Yeah.
We'd have to calculate how all the features are related, which is a computational nightmare, especially with lots of features. This naive assumption makes the math a lot easier to handle.
So that big, scary Bayes theorem formula becomes more friendly because of it.
Exactly. By assuming independence, that probability of seeing all our features, let's say they're named by 1, by 2, and so on, all the way to xn given a specific class, just becomes the product of each individual feature's probability given that class.
Okay, so it's like breaking down a big problem into smaller, easier chunks. But how do we actually use all these calculated probabilities to classify something new?
That's where MAP estimation comes in. Maximum a posteriori, or MAP for short.
Yeah.
We take a new piece of data, something we haven't seen before, and we basically run the numbers for each possible class using our simplified Bayes theorem. Whichever class gets the highest probability, that's our pick.
Makes sense. We're picking the winner based on who's got the best odds according to the evidence. Now, our sources mentioned there are different types of naive Bayes classifiers. What's the difference between them?
It's all about the assumptions they make about how our features are distributed within each class. We're still assuming features are independent given the class, but how we actually calculate the probability of seeing a specific feature value for a given class, that's where things differ.
Okay, so let's break down these different flavors. First up, Gaussian naive Bayes. What's that all about?
Gaussian, that's when our features are continuous numbers, things you can measure, like a person's height, the temperature outside, stuff like that. And it assumes that those values within each class follow a normal distribution, the bell curve.
So like heights of men tend to cluster around a certain average and heights of women around another average.
Right, so we estimate those averages, the means, and also how spread out the values are, the variance, for each class and each feature. Then, with a new data point, we see where it fits best on those curves.
The Scikit-learn docs even use that iris data set as an example, right? With the measurements of flower petals and stuff?
Yep, that's a classic example of how Gaussian and B can classify different types of irises based on those continuous features. By looking at how those measurements are distributed for each type, we can figure out which type a new flower is most likely to be.
Cool. Now, multinomial naive Bayes. This one sounds like it deals with counting things.
You got it. This one's really popular for text data. It assumes our data comes from a multinomial distribution, which is basically a way to model counts of different events. So in text, we're counting how many times each word appears in a document.
So for classifying news articles, we'd see how often words like sports, politics, or business show up in articles from each category.
Exactly. But there's a catch.
Yeah.
What if a new article uses a word we've never seen in that category before? That'd give it a probability of 0, which messes things up. So we use something called smoothing to avoid that. Yeah, it's like adding a tiny imaginary count to every word, even those we haven't seen, so they don't have 0 probability. There are different ways to do it, like Laplace smoothing, which adds 1 to every count, or Lidstone smoothing, which adds a fraction.
So, like, giving everything a tiny chance, just in case, makes sense. Now, complement naive Bayes, that sounds like it's doing the opposite of something.
It kind of is. It's really useful when you have imbalanced data sets, where one class has way more examples than the others. Instead of looking at what makes a class unique, it looks at what's not typical for that class.
So it learns what makes something not belong to a category. I guess that could be helpful when one category dominates the data. Our sources said it often does better than regular multinomial ND in text classification.
It can be a lot more stable, especially when things are uneven. It basically figures out which terms are least likely to show up in documents from a specific class.
Interesting strategy. Okay, what about Bernoulli naive Bayes? Bernoulli usually deals with yes-no kind of stuff, right?
Right on. Bernoulli NB is for when our features are binary, meaning they're either present or absent. Like, does this email contain the word free? Yes or no. We don't care about how many times it appears, just whether it's there or not.
So it's about presence or absence, not frequency. And the documentation mentioned that it penalizes the lack of a feature that's usually strong evidence for a class.
Exactly. Like if the word Viagra almost always shows up in spam emails and it's missing from a new email, Bernoulli NB takes note. It's often better with shorter documents where just the presence or absence of certain words is more important than how often they appear.
Gotcha. And finally, categorical naive Bayes. Does that handle features with multiple categories?
You got it. It's for when each feature has a limited number of possible values, like colors.
Ah.
Red, blue, green, or transportation types. Car, bus, train. And it assumes that seeing a certain category in one feature doesn't affect the probabilities for other features, given the class.
So it figures out, for each category within each feature, how likely it is to see that category for each class. And the formula uses counts of how often those categories appear for each class, right?
Right. And it also uses smoothing, just in case some categories haven't been seen with certain classes in the training data. But one thing to remember is, for categorical MB, you usually need to encode those categories into numbers before you can use it.
Wow, that's a lot of different types of naive Bayes, each with its own quirks and strengths. But let's go back to that big question. How can this whole naive approach actually work so well in real life, especially if it's making such a big simplification about independence?
It is a bit of a puzzle, isn't it? But honestly, naive Bayes has a pretty impressive track record, especially in things like text classification and filtering out spam. And one reason is it's surprisingly efficient with data. It doesn't need massive amounts of training data to learn those probabilities compared to more complex models.
That's huge, especially if getting labeled data is difficult or expensive.
Absolutely. And remember that independence assumption. It makes things super fast, both for training and making predictions. We don't have to figure out how all the features are related. We just look at each one separately. And this also helps with something called the curse of dimensionality, which basically means things get exponentially harder as you add more and more features. Naive Bayes is less sensitive to that.
So it's a win-win. Less data needed and faster processing. Pretty powerful stuff.
It is. But there's a catch. While naive Bayes is good at picking the right category, making those classifications, it's not so great at estimating the actual probabilities. So those numbers it spits out might not be super accurate in terms of how certain it is.
So it might correctly say an email is spam, but that 99% certainty score, maybe take that with a grain of salt.
Exactly. And there's some interesting theory about why it works so well, even with that quirk. The key idea is, for classification, all we really need is to get the order right. If the model consistently picks the most likely class, even if the probabilities are a bit off, then it's doing its job.
So getting the ranking right is more important than getting the exact numbers.
Yep, but there are limitations. That independence assumption, it can be a problem when features are strongly related in the real world. In those cases, models that can capture those relationships, like logistic regression or decision trees, they might do a better job.
Like, if certain words almost always appear together, ignoring that connection could make the model miss important patterns.
Precisely. And remember that zero frequency problem. If a feature never shows up with a specific class in the training data, we get a probability of 0, which really messes things up. Smoothing helps, but it's something to watch out for. And another thing is, with just yes-no features, naive Bayes can only learn linear boundaries. So if the classes can't be separated by a straight line or its higher dimensional equivalent, it's not going to be the best choice.
Right, so powerful tool, lots of uses, but definitely not a magic bullet. Let's talk about some specific examples to see how this all works in practice. We've mentioned spam filtering a lot. What's actually happening there?
Basically, we treat each email like a document, and the words in it are our features. We train a naive Bayes classifier, often Multinomial or Bernoulli, on a bunch of emails that are already labeled as spam or not spam. The classifier learns how likely each word is to appear in each type of email.
So, like, the word Viagra is probably more common in spam.
Yeah, exactly. Then, with a new email, it looks at the words and uses those learned probabilities to figure out if it's more likely to be spam or not.
Classic example. What about other kinds of document classification?
Pretty similar idea. If we want to automatically sort news articles into sports, business, politics, and so on, we train a naive Bayes classifier on a bunch of labeled articles. It learns which words are typical for each topic, and then uses that knowledge to classify new articles based on their words.
And what about understanding sentiment in text? Like, is a customer review positive or negative?
Same principle applies. We treat reviews or social media posts like documents, words are our features. We train the classifier on labeled examples. It learns which words are associated with positive, negative, or neutral sentiment, and then uses that to classify new text.
Our sources even had an example of using Gaussian naive Bayes to classify people as male or female based on things like height, weight, and foot size.
Yeah, that's a good illustration of how Gaussian B works with continuous data. They had some made-up data with measurements for a bunch of people, calculated the averages, and spread for each feature for both men and women. Then, with new measurements, they calculated the probability of being male or female based on those learned distributions and picked the category with the higher probability.
It's amazing how it can still give a reasonable answer, even if, like, height and weight aren't totally independent in real life.
It is. Now, thinking about how naive Bayes relates to other machine learning models, our sources talk about logistic regression.
Yeah, it said they're a generative discriminative pair for discrete inputs. What does that even mean?
Basically, naive Bayes is generative because it tries to model how the data itself was created. Logistic regression, on the other hand, is discriminative because it just focuses on learning the boundary between classes.
And there's a theorem saying that for binary features, any decision boundary learned by naive Bayes can also be learned by logistic regression.
That's right. But the interesting thing is, sometimes, especially when data is limited, naive Bayes can actually do better than logistic regression. It can reach its best performance with less data.
Goes back to that data efficiency. Now, what about out-of-core learning? Our sources mentioned that briefly.
Oh, that's for dealing with massive data sets that are too big to fit in your computer's memory all at once. Some naive Bayes implementations, like in Scikit-learn, have a special function called partial fit. It lets you train the model in chunks, feeding it bits of the data at a time.
So it's like instead of eating a whole cake at once, you eat it slice by slice.
Perfect analogy. Now, one of those research papers we looked at had a pretty surprising finding about feature dependencies. They said the accuracy of naive Bayes isn't directly tied to how much those features depend on each other, at least not when measured in a certain way.
Yeah, that was a head scratcher. I figured more dependencies, worse performance, right?
Turns out it's more complicated than that. What matters more is the information loss caused by ignoring those dependencies. How much information about the class do we lose by pretending the features are independent?
Okay, so it's not just about whether they're dependent, but about what information is lost by ignoring that dependence.
Right. And get this, they found that naive Bayes can actually work well in two situations that seem opposite. When features are totally independent, which is what it assumes, but also when they're highly dependent, meaning one feature basically tells you everything about the other.
So if they're giving the same information, it doesn't matter as much if they're treated separately.
Exactly. It's when those dependencies are more complex, providing extra information beyond what each feature gives you individually, that's when naive Bayes struggles. And they also found that having features with low entropy, meaning their values are pretty predictable for a given class, can help it perform well.
So even though it's making this simplifying assumption, the data itself can make it work in surprising ways.
Absolutely.
Yeah.
It shows that understanding the characteristics of your data is crucial.
All right, wrapping it all up, naive Bayes. Simple but powerful. It's fast, works well with limited data, and handles high dimensionality like a champ. But we gotta be aware of the limitations, that naive assumption, the fact that those probabilities might not be super accurate, and the zero frequency issue.
It's a trade-off, right? Simplicity for efficiency and often surprisingly good results.
And that stuff about feature dependencies really makes you think, right? It challenges those intuitions about how models work.
Yeah, sometimes the simplest approach can be more robust than you might think.
So, here's a thought for you, dear listener. Maybe this naive approach is telling us something about decision-making in general. Maybe sometimes focusing on the most important factors, even if it means ignoring some complexity, can lead to better outcomes. Something to ponder, right? Thanks for diving deep with us today.